So we're continuing on problem 10 on page 245. But before that, I want to show you a picture of my trip to Disney World, where I stayed at the Disney's Animal Kingdom Lodge. Okay, and I took a picture of what I saw outside my balcony. Now take a look at this. Let's see. Let me zoom in here. Now as you can see that this is why is this tilted? Okay, this is my balcony. Okay, here's the balcony railing, and look out there. What do you see? And notice that thing over there. Okay, it was really cool. Let me make it bigger. And guess what was just outside my balcony window? There is a 1, 2, 3, 4 giraffes, and 1, 2, 3 zebras right there outside my balcony. It was just I'm not really that much into animals, but that was, I have to admit, that was quite amazing. It really is like living in Africa or something. So that I thought was very neat, and I want to show you this picture. And that is that. Okay. So having said that, let's continue with problem 10. So problem 10 on page 245, we are supposed to use the equation 8, which is this one right here. Where's equation 8? Okay, this thing right here. Okay, the standard transformation equation on page 243. And we're supposed to use this equation here to show something, to show that the area of surface of revolution is that formula that they gave us. All right. So let's do that. The problem 10, okay? So we'll let P equal to 1 because we're just calculating the area. And then we're going to calculate J1, J2, and J3 because X and Y are given as such, okay? So we'll calculate the J1, J2, and J3 as defined on page 243. That is all the stuff here, which is a bit of a grunt work. And so we'll calculate all these three things. Then we calculate what the square root is, and then something good might come of it. So let me see. I have it done here, right? Yeah. So I calculated what J1, J2. I think there's only J1, J2. There's no J3 here, I guess. Is there a J3 here? Yes, there. Let's see. J1 is this thing. Yeah, there is a J3 here. Here's J3. J2 is over here. But anyway, we go through all that grunt work based on this definition, and then we calculate what D is, and after all that, D comes out to be U times square root of F prime squared, exactly like it says. And therefore, we plug it into the equation, and everything comes out like it should. So there is that F. And then that's about it. Is that what we're looking for? Yeah. And also the integration during the integration, let's see. Yeah, because the integral of u goes from 0 to 2 pi, so then the final answer came out properly, like this. Yeah, so then we have, right, because v got integrated, v goes from 0 to 2 pi, and v is not in the integrand, so then we can take the 2 pi out, and that is our answer for problem 10. All right, okay. So next, let's consider problem 12 and find the area of some torus. But before I do problem 10, I did graph it somewhat, so I want to show you what that looks like. Okay, and so we have a function f of z equals to f of u. As an example here, I let u equal to z squared, okay? And then, so I let z equal to u squared, which is the f of u, and then I spin it around the z-axis, so I got a bow-shaped thing. This is just an example. Let's say a sample where f of u is u squared, then I spin it around, and then I get this bow-shaped thing. And yeah, and then everything makes sense that way. This is just a quick illustration of a sample. And then, of course, at each point, if we consider each point will spin around like become a round disk, okay, circular disk. Yeah, but anyway, I think that's all there is worth mentioning there. And let's consider the torus, which is on the next thing. Now, to calculate the torus, we'll use the problem 10 that we just did. So we need to figure out what f of u is, right? The function then, the function is to calculate f of u as a function of z, then the torus is something that you go off, right? You spin around the whole circle. I only drew half of it here, where it's centered at R0, and it's a circle centered at R0 with centered at big R0 and with radius small r, which means the formula would be using the formula of the circle with a center that's at R0, then you come up with this c equal to square root of r squared minus r minus u squared very quickly, okay? So that is the function f of u to represent this, which represents this hemisphere. The other half is the same. We'll just double it, because right now we're calculating the area of the torus. So then, so if f of u is this, then f prime of u is this thing, okay? And then plugging it into the formula of problem 10, then we get this thing right here. And so the rest of the work is just about how we're going to integrate this thing. Now, I have this thing plotted into decimals, of course, because that makes a very nice graph. What problem is that? 12? Let me find problem 12. I am not seeing it. Oh, I know. I labeled it problem 11. Okay, so here it is. So I plotted the torus in decimals 3D. Remember that torus has a big R and small r. Big R is the major radius, where small r is how big around the minor radius, okay, of the little cross-section circle. Big R is its main radius, what the radius of the torus is. It measures to the middle of the torus like that. And so anyway, I have a sample of a torus here, which looks just like a donut, okay? Yeah, anyway, and then z equal to f of u, as you can see right there, is that semicircle, let's say. Z equal to f of u is right there, and if you spin it clear around, then you will get the donut. Now, I also blow it up just this part, okay? Blow it up in here, the little part of the donut, where z equal to, on top, I have written, oops, the other side. On top, I have written where the formula for z is this thing. Please verify this yourself, okay? It's just the hemisphere that's centered, that's a bit off-centered. That's centered at r comma 0. If you, yeah. Anyway, so, and then you spin this thing around around the z-axis, you'll get to the result. Now, so this blue line length is r, okay? This point is, and then the orange line is small r. So this point here, the total length here is r plus r, and so on. And so all this is pretty good. And now we are just stuck with doing the integration. Now the integration turns out to be not that obvious. So I ended up doing the indefinite integral on the Wolfram calculator, and it gave me this answer. Okay, and once I got the indefinite integral, then I had to do it by hand, plugging stuff in, which is what I did. Okay, and which didn't turn out to be too bad, because stuff was going to 0. And so things was disappearing on me. Let me wait for this thing to focus in a little bit. There we go. And so once we calculate, here's the antiderivative, okay? And I was being extra careful. So what I did is I did the integration from 0 to minus r, and then from r minus r to 0, I think it is, or. Well, whatever. I did it in 2 parts because I was worried that during the integration it might be a positive part and a negative part, and ended up with 0. But that didn't happen, okay? And it's not necessary. I don't think it's necessary to do it integration in 2 parts. So each part is the same. I end up, so it's probably not necessary. Just do the original integration like this, and that should have worked anyway. Yeah, so that is how the area of the torus calculated under this formula. We have also done the, well, I don't know if we have done it. I think in the past I more or less skipped it because it wasn't that exciting. But I'm not skipping it this time. The area of torus was calculated several times throughout the learning of calculus, and this one again shows that our formulas are working because we know what the area is, so we're testing it by finding the area of the torus to see if the formula works out. Because if it doesn't, then something is not going right. Okay, but it does work, so we're good. I don't know if I show you the integration formula clearly, so I'll show it to you one more time. Okay, that's just what I typed into the Wolfram calculator, and that's what it said. And following this formula, I was able to get the right answer. There's probably a way to integrate this, but I wasn't going to bother with it. And yeah, it's too much work. As it is, this stuff is taking me a long time to do. So next, let's consider problem 14, which is actually something that I already did. So we're just calculating the Jacobians for the spherical and the cylindrical coordinates, I guess. And so I did that again. And as you can see, it does end up being r squared sine phi because all the stuff ended up collapsing into, there's a bunch of sine squared plus cosine squared equal to 1 and stuff like that. It ended up being this, I guess. Anyway, it ended up being this thing, okay? Assuming that all the stuff is right, and I hope it is. So anyway, and the cylindrical coordinates is much simpler because there are 2 zeros, so the calculating the determinant is much simpler and does become r like the book says. So anyway, problem 14 is when I was at Disney World, okay, and I said 14 is the first day where I did it in the hotel. See, I wrote down right here, WDW, that stands for Walt Disney World. And so I did it in the hotel when I was resting from my going out. And it was very nice, okay? The Disney hotels are very beautiful, right? And I'm sitting there doing math while my kids might be taking a nap or something. That was totally awesome. Anyway, so that is, let's move on to problem 15. I was having trouble with problem 15. You know, there's just so many symbols, and then I couldn't get it to come out, okay? I mean, the question is very simple. We're supposed to show that there's a bunch of conditions, right, that look somewhat complicated, and then we're supposed to show the Jacobian equals to that thing with a bunch of square roots, and it seems like a bunch of tedious algebra, and I couldn't get it to come out. So what I did is I decided to do problem 16 first, which is just a matter of verifying that problem 15 is correct. So I was hoping that would give me some inspiration, and so I did that, which is that was quick enough. We just do the similar thing, calculating what C1, C2, C3 is, and multiply them together, and there it is indeed the r squared sine phi. But that didn't really help me. Okay, so I continued to work on problem 15, and continue to not be able to do it. And then yeah, see, there's a whole page here, and then there's another whole page here, and then it got to be the next day. Then I came home from Hollywood Studios early because I had an idea. I thought maybe I can do it. Well, I couldn't. Okay, so by then I decided to ask AI, how do you do this? And the AI said something that was very obvious. It says that the Jacobian is a determinant. The determinant is the volume of a parallelepiped. Okay, and when I noticed that, then I realized that, and then those three equations of stuff multiplying and then equals 0. That's just 3 vectors dot product. The dot product of these 3 things are 0, which means that something is orthogonal. Okay. Now knowing that, then I suddenly realized how to do this problem. It's actually very simple after me struggling with it for so long. So what happened is that if you look at problem 11 on page 70, the volume of a parallelepiped is exactly the determinant RST, where RST are vectors of the edges of the parallelepiped. For example, that is our Jacobian equals to RST, where the first row is R, okay, and then the second row is S, and the third row is T. Why do I have K here? That's supposed to be H. Let me fix that. All right, I got it. So these are if these are RST, then the three equations we gave, just all that says is R dot S equal to 0, S dot T equal to 0, and T dot R equal to 0 is what these three equations are talking about. And look at what we're given here, okay? The equations that are given here. It says, let's see, yeah, see, and G1, and that is, and let me see. Okay, now let's put these two things together. Okay, let's see. So here is the other side. Here is the formula for the that we are given. It says G1, G2, H1, H2, and K1, K2 is 0. So if over here, that means G1, H1, K1 is R, G2, H2, K2 is S. That means R dot S is 0, etc. Okay, so these vectors are all perpendicular. They're all orthogonal, which means the volume of the parallelepiped is the determinant of this thing. And being that they are perpendicular, then the volume is simply length times width times height, and which is C1, C2, C3, when each Ci is Gi squared plus Hi squared plus Ki squared. Okay, now that's all there is to it. So we just pulled out some old trick from this is problem 11 on page 70 or something. See, and we did this back in page 70, but we also did this in basic calculus. I think it was calculus 2 or something, where the volume of the parallelepiped, which you can Google, okay, the volume of a parallelepiped is R dot S cross T, or the determinant of RST of the matrix. And of course, when these things are perpendicular, being that it's a parallelepiped, and that means that its volume, then if all three vectors are perpendicular, then it's just a box. And it's the volume, which is the Jacobian, is the length times width times height. So that was quite interesting, okay? And I went through all that algebra and could not get it to come out. It was such a giant mess. But anyway, so I got this to eventually to work. So that was very good, okay? And that's that. So next, so I already gone through for problem 16, which is just a verification problem 15. And then so let's move on to problem 17. The 17 is, let me put this back. So problem 17 says we need to find the area of a region. That region is perfectly easy to find. I could have done this in algebra, right? But we're going to integrate in the UV plane. That is, we're going to use the transformation 9 on page 244, which is, well, okay, what's that? And in other words, we're going to use this transformation and calculate the area the hard way, okay? And that's on page 244. This particular transformation is the transformation 9. So let's do that. We have, all right, so what does the transformation do? To using the transformation, we're supposed to calculate the disk shape, right? That's the circle with a hole cut out. Let's see, let me look at, what does it say again? Okay, we are calculating the area of the whole thing, okay? And by using the transformation. But before, we noticed that the transformation, what it did is it stretched the thing, that is, and doubled its length, well, so to speak, or doubled its angular turn. So in other words, the transformation, which I have written right here for problem 17, the transformation will take this thing right here, which is half of one, and bend it into this entire shape, okay? And you can confirm it where you notice that the red side and the green side, the edges, okay, will be combined into in together into one, because it just take the whole thing and pulled it and folded it together. So, and well, without doubling, okay, they just touched right here. So then, so that's the but it is still a one-to-one transformation, except for that the final result where the green and the red put together. But on the inside, however, it is indeed one-to-one. So we use the calculation by calculating the Jacobian, and then stick it in the area formula by putting the Jacobian in the UV universe right here. Okay, and then use the polar coordinates to calculate this thing. So then what we end up having is the calculating bipolar coordinates of this formula right here. We have then dsuv is going to be r dr d theta, and then u squared plus v squared is just r squared. I'm converting things into polar coordinates, and then the r goes from 1 to 2. Okay, that's the original, that's the UV dimension. This one isn't 1 to 2, but this one is. And then when we calculate this simple integration, then things came out pretty good. I don't know what this is, but eventually I got this answer, and that turns out to be correct. So that's good. Yeah, it checked out. So that's problem 17. Now problem 18 is quick enough. It says it's a transformation that we just saw. It's a transformation that we just saw one-to-one. The answer is no, because everything got wrapped around twice, and that's all I have to say about that. Now where is it anyway? Where did I say that? Give me a second here. Okay, that's all I wrote. See, problem 18. No, it's not one-to-one because it went around twice. And that's all there is to say about it. And then next, so let's consider problem 19. Problem 19 is much more tedious. Longer anyway. The principle is easy enough. Okay, we have a bunch of weird stuff. We have x equals some kind of area, which is fine. It's parametrically represented. That's okay. Where x is x of s plus some s u, and then y is y of s cosine u, and z is sine u. And what is this area? Now we can totally do that with just one catch. Okay, and the problem is there's a derivative in here. That is, big X is represented by x of s, and then y prime of s, and big Y is y of s, and then x minus x prime of s. What's with the derivatives right inside the parametric definition, which is not something we've seen that much, if at all. So and then there's also a condition where x prime plus y prime equals to 1. And that's what makes the algebra weird. Okay, how are we gonna do that? So let's try to do it anyway. Okay, so see what we got out of it. We follow the formula, which is the formula on page 243, I think. Yes, which is this formula right here. Okay, we're gonna follow the standard formula. That is, we calculate the area by sticking in the d. Right, the d right here. What is the d? Is, well, whatever it is, we're gonna stick it in, okay? And getting the d to come out, then it should be okay. And that, so the principle is simple enough. The question is, how are we gonna calculate the d, the big D, when we have all these weird derivatives inside the very definition? So that's what we're gonna struggle against. And so to do that, then we will calculate things. Okay, here's J1 based on these definitions. We calculate what is J1, what is J2, what is J3, and they equal to J1 and J2 are shorter, J3 is longer, right? And so then we know this much, and that is x prime squared plus y prime squared is equal to 1. And then we can take the derivative of this to get this next relationship. That is x prime x double prime plus y prime y double prime is 0. Okay, that might come in handy. It better. Okay, otherwise what's the point of having this? So then we have, but the next thing is we need to calculate d equals the square root of sum of squares of these j's. So let's do that. So J1 is squared, okay, that's looking longer. J2 squared is also looking longer. And then, So this, and we need to figure out what J3 squared is. But before that, being that these two are already very long, I decided to calculate just these two first. Okay, so let's calculate what is J1 squared plus J2 squared. Okay, so J1 squared plus J2 squared, once we did that, and then we noticed that it contains x squared plus y squared, the primes, the derivatives equal, which we can set that as 1 because that's given as 1 here. That's so far so good. But what about the rest of the stuff? Okay, I had no clue what to do with the rest of the stuff. So eventually I asked Google, and Google tells me a trick. Okay, there's a quick, easy trick that we can apply, and that we can take care of this matter. And the trick is called the 2D version of the Lagrange Identity, which is I will show you here. Okay, and so here's what AI told me. We'll use the 2D version of the Lagrange Identity, which says that this equals to that. Okay, and then if we let A is x prime and so on, then we will get this equation equals to this thing right here. So what we have in here is the x double prime plus y double primed. Okay, and this is equal to 1 as given. So we'll have this thing equals to this thing. And that's what I stuffed in here, and then everything come out beautifully. And let's see. All right, so let's see how that goes. And following the Lagrange identity, right? And we plugged it in. So by Lagrange identity, this thing, this is equal to 1. Plugging stuff in this Lagrange identity equation. Then this equals to 1 as given a little earlier here. This thing is what we need because it was in the J1 plus J2 formula, and I don't know what that is. So by Lagrange identity, we got this thing, which is that, is equal to this following Lagrange's identity, and this happens to be 0 because we calculated it by taking the derivative of this thing. Okay, so that part equal to 0, and then plus whatever this is. So we'll call this kappa. Okay, so the inside here kappa. So this is kappa squared, and the reason I call it kappa is because the AI calls it kappa. So I just follow right along and call it kappa. And we got a formula with kappa in it. Okay, so far so good. And that we have only done J1 plus J2, but we have already cut through the meat of the matter. Okay, the rest is going to come out very nicely. So now that we have and then so rewriting J1 and J2 by substituting this thing right here is equal to kappa squared. Okay, in other words, put kappa squared right here in this formula. Okay, because that's what the Lagrange identity tells us. 1 times this thing equal to 0 plus kappa squared. So this thing is kappa squared, which we plug it in right here. And so J1 plus J2 equal to cosine u, following this formula, times 1 plus 2 kappa, so that's also kappa. And this thing is kappa squared, and it's that neat. And then, anyway, so 2 kappa cosine u, okay, following this formula, and then plus kappa squared cosine u squared, which happens to be a perfect square. This part is. So we'll turn it into a kappa squared. And, okay, and remember this. We will, Anyway, so this is J1 plus J2. And next, let's work on J3. J3 is, from what we had before, is... J3, did we say anything about J3 before? Yeah, J3 is copied from up here. So J3 and rewriting it down here, which we have a bunch of stuff. And among them, J3 has minus y prime squared and minus x prime squared. So that just combines to be just minus sine u, being the x prime plus y prime is 1 squared, that is. So that is, and then the rest of it is that thing minus that thing, which happens to be kappa times sine u times cosine u. Okay, they have sine u and cosine u on both sides. So we're doing a bunch of algebra here, but eventually we got that. So now we have J1 squared and J2 squared, which is this one circled in red, and J3 squared circled in red here. So let's put them all together, which is this thing right here, okay, and that equals to d squared, which if you look at this thing very, very carefully, you notice that cosine square u plus sine square u disappeared, becomes 1. So d squared is just 1 plus kappa cosine u squared. So that's what d is, okay? Where kappa, as we have defined earlier, is x prime y double prime minus y prime x double prime, which I wrote down again right here. All right, so now we got a d, and the d doesn't look too bad, okay? And unless, except for the kappa bit, because the kappa doesn't look that simple, but we'll deal with it. So let's take the double integral following the formula. The area that we were looking for is double integral du ds, okay? And which is, and we are given that u goes from 0 to 2 pi, s goes from 0 to L, and we're going to integrate this thing. So we'll divide it into 2 parts. So if we divide it into 2 parts, first we'll integrate the 1, okay? That's the easy part, right? Integrating the 1, that will give us the 2 pi L. And then, well, what about this? And how are we supposed to integrate kappa? And where is all this weird stuff? Well, we don't have to integrate kappa because there's the cosine u there, okay? Integrating cosine u from 0 to 2 pi is 0. So then we can ignore the integral of kappa and all that is 0, so ignore all of it. And then the answer is 2 pi L, which checks out to be correct. Okay, that's that. And the next question we have to wonder about is this curve. Okay, that is x of s and y of s. The curve, what is it? And which is what the book asks. Like, what is this curve? Actually, I don't think he even answered his own question. But we're going to do whatever the answer in the back says, okay? So the curve is something that goes around, and it is, well, whatever, okay? It is arc length parameterization of some curve, which is fine. And then what I want to mention that the curve, we can calculate the curve by calculating this formula right here, where the curve is the curve is the small xs and small ys, okay? But the thing is that's the tracing curve. That's not the surface itself. Now the surface is the big xyz, and the surface, as we can see, that if we were to calculate big X minus x of s and big Y minus y of s and big Z minus 0, that and plugging in what we are given, these formulas, right? Yeah, the original formulas, okay? If we do big X minus small x of s, then we have this thing and then square it. So it'd be this thing squared, and similarly this one, this thing squared, and so on. If we do that, then you realize that it equals to, let's see, where to go. Okay, so if we do all that, it equals that thing squared plus that thing squared plus that thing squared equals to 1. Okay, also because remember, y prime plus x prime as the squares equals to 1, and everything kind of, and the sine squares and the cosine squares and whatnot. Anyway, it all ended up being just 1, which what that means is that the surface xyz is on the unit sphere that is centered at x of s, y of s, and 0. And so then, so this thing, this is each one for s is some kind of a curve, is some kind of the big X, big Y, big Z are on these spheres, and also Z can be 1. Okay, so for fixed s, if you fix s, then the xyz becomes a curve. And for each s, okay, if you fix s at a certain point, then each one is some curve on the surface, and you notice that it is possible for z to be 1, and being that it's on the unit sphere, okay. So z can easily be 1, and then but that's not all. And also the big xyz for each fixed s is a plane curve. Okay, it's a plane curve that goes through, that cuts through is on the plane curve, and it's also on the sphere, which means is a circle, because it also goes through the poles, because z can be 1. And why can z be 1? Because z is defined as sine of u, right? Let's see, where's the thing? Right here. Yeah, z is sine u. So, and u goes from 0 to 2 pi, so z is sometimes on top of the sphere, and some at a positive 1 and sometimes negative 1. Now, given that, then I'm saying that the xyz is a plane curve for each fixed s. And how do I know that? That is by using theorem 3 on page 73, where it gives the formula that if a curve has this quality, that is x prime, x double prime, x triple prime, the determinant of these these things equal to 0, which I calculated here, and this determinant is 0 because column 1 is the same as column 3, except negative. Okay, if you have identical columns, then the determinant is 0. And I also want to show you theorem 3 and this plane curve theorem. So here is theorem 3 on page 73. Okay, here's theorem 3. We have, and to show something is a plane curve, then we have to have that relationship right there where the x's are vectors. And so please look that up to see why that is the case. And the reason I'm doing this is because the answer says that says a bunch of stuff. Okay, now the answer at the back of the book says, this is let's see, what am I doing here? Problem 19, I mean, right here. Okay, so the problem 19, the length is 2 pi L. The surface area is 2 pi L, which we have. It says the surface is generated by moving a unit circle. So we just proved that the surface on the unit sphere. And the circle is, and how is it a circle? If it's a circle, then it has to be a plane curve. All circles are plane curves, which is why I had to prove that this thing is a plane curve by using the plane curve formula on page 73, theorem 3, to prove that this is a plane curve. So if it's a plane curve that is on the surface of the unit sphere and goes through the poles, it goes through the top and the bottom of the sphere, is just a great circle. So that's how I prove that it must be a circle. And then the next part that the book says that it is not just a circle, but it's a unit circle that is normal to and with center on. Okay, read this carefully. Unit circle normal to and with center on the curve x equal to x of s and y equal to y of s, and where z is 0. So that is what I'm trying to prove here. Okay, and so we'll prove everything the book says. All right, so the next page is the plane of the circle. We'll call it gamma. Okay, the plane of the circle is just a plane, but gamma is its normal. Okay, and then gamma then is given as x prime cross x double prime, and this is given on page 95. The definition of gamma. Then if you calculate gamma, then you notice that by calculating x prime and x double prime, which is this stuff, and then you realize the gamma of the circle, the circle's plane. Okay, so gamma is going to be equal to minus x prime I and minus y prime j. Yeah, that's the direction. Now the curve x of s, y of s has tangent x prime of s, y prime of s, which means gamma and the curve are in parallel directions. They're in the same, or you can say opposite. It doesn't matter, either one. The point is they're parallel, right? So gamma is, and which means that the plane is perpendicular to the, or orthogonal or normal to the curve, and that is yep. So that is, let me show you that again so you can see that better. And that is then that is okay. So that is that. Is that on page 95? Well, whatever it is on the page that we looked at the normal to surface vectors. It's probably on page 95. It's good enough. And yeah. So let me show you this stuff again. So you have. Let's see, maybe I should show you the whole page. Nah, let's show you. Okay, I'll show you the whole page here, and then zoom in to see the half of page, so that it's easier to see. That is the top half of problem 19, and then the second half of problem 19. Where did I stop there? J3, okay, I stopped at J3. Yeah, that's good enough. And then the last bit, I'll show that to you again. Okay, so that should be good, and that marks the end of this extremely long section. It seems like it has a lot of interesting problems that I enjoy doing, and yeah, and I did a part of this starting at problem 14 in Disney World and thoroughly enjoyed it. And that should be the end of this section.